We'd like to invite our next speaker, Tamara Grossman. If we can.
All right.
Tamara.
Can you see my screen?
Yep, your stream is good. So Lancelot's from Imperial College, London, and the talk will be on global brain theory, stochastic thermodynamics, and applications to autonomous agents.
Great. All right. Thank you very much for coming, and thank you very much for the opportunity. So just a question before I get started. Can you see the arm moving here or not?
The mouse is moving.
Do you know how I can share it? No.
Your mouse is moving now.
Right, because I have a second PowerPoint with a video. Can you see it or not?
Not right this second.
Okay. Well, I'll do without the video, and then maybe I'll be able to fix it. All right. Well, thank you very much for coming, and thank you for the invitation. So I'm first going to give you an outline of what my research is about. So my research is at the intersection of mathematics, neuroscience, and artificial intelligence. And as you know, much research goes into math and artificial intelligence, or neuroscience and artificial intelligence. The problem is the latter has remained mostly qualitative, just because the brain is so complex that it has been difficult to draw many quantitative insights. So as a result, traditionally, there has been very few mathematicians working inside neuroscience and artificial intelligence at the same time. But now, in the last decade, neuroscience advances have described brain function with higher mathematical sophistication, revealing principles that can be applied elsewhere. And my goal today will be to summarize some of those developments. So to set the stage, I'm just going to talk about some global brain theories that have received a lot of attention and empirical validation. So one of the goals of computational neuroscience is to describe globally what the brain is doing using mathematics. All the theories that exist so far draw from existing fields. So for example, the Bayesian brain hypothesis, which postulates that the brain infers its environment from its sensations using Bayesian inference. Now there's also predictive coding, which says that the brain makes predictions and minimizes the prediction error. So the error between the predictions and what actually happens. The expected utility theory says that the brain chooses actions that maximize cumulative future reward. So this is basically reinforcement learning. And there's also homeostasis, which is much more biologically grounded, which says that the brain maintains the entropy of its sensations bounded. So crucially, in all or almost all theories of brain function, there's one theme that keeps coming again and again, and this is optimization. So the brain is optimizing something, and one may ask, what is being optimized? So depending on the theory, this can be value, expected reward, expected utility, and so on, or surprise, which would be expected cost, so the complement of value, prediction error, and so on. Now I'm going to talk about the free energy principle, which is the brain theory that I'm currently working on and I'm most interested in. So before I really explain what the free energy principle is about, I'll refresh what Bayesian inference is and introduce some notation. So free energy principle postulates that the brain performs a variation of Bayesian inference. So Bayesian inference. In this talk, I will denote by E, capital E, the state of the environment, which is going to be a random variable over Euclidean space. and I will denote by B the blanket states. So you'll see later why this name of blanket states makes sense. So the blanket states are the states of the agent's sensations and muscles. And I will also assume that this is a random variable over Euclidean space. Now, a generative model is a probability density over states of the environment and blanket states. So it consists of a prior over states of the environment here and a likelihood function that says if this is what is going on in the environment, then this would be what my sensations would be. So to give you a concrete example, we think that the brain has a generative model of how 3D scenes in the environment cause 2D images on the retina. And so this is nice because then given some blanket states, little b, so for example, your 2D image on the retina or what you're currently hearing, you can infer the external states, you can infer what caused this 2D image on your retina using Bayes' rule. So Bayes' rule is this very nice and simple rule that tells you if you see something, then what is the probability of this 3D scene happening out there? So the problem with Bayes' rule is that this posterior that you can find again here is not simple to calculate. It's in fact very, very difficult. And for generative models in real world applications, it's often very hard to compute this posterior. So just to recall, E here is the state of the environment, and B are the agent sensations and muscular activation, so blanket states. So variational Bayesian inference enables you to solve the Bayesian inference problem by just approximating the true posterior that's here with the approximate posterior that's Q. So you're basically minimizing a KL divergence or a discrepancy. It's not really a distance, but you can think of it as a distance. So you're minimizing the distance between your inference over external states with the true external state, so the true posterior. So by minimizing the scale divergence, you're making your inference as good as possible. And crucially, even if you're not able to directly compute the posterior, it's often much easier to minimize the scale divergence. So I'm going to define by S this quantity here. And the crucial result is that the minimum of the expected free energy, this quantity F, is going to be the best fit approximate posterior. So the minimum of the free energy gives you your best inference about what's actually out there. Right. So depending on your background, I call this a free energy, but you can call this a relative entropy, a KL divergence, or an evidence lower bound if you're in machine learning. So crucially, optimizing this free energy on a space of probability measures enables you to approximate the true posterior. So the free energy has many interesting properties that we'll talk about now. So this is all purely statistics and statistical inference. So I can define the model evidence P of B, which basically scores the goodness of your model in relation to the data that you currently have. Now, crucially, the free energy upper bounds the surprise of blanket states. So by surprise, I mean the negative log probability of B, or the negative log model evidence. And so you have equality if and only if your inference is exact, if and only if you're at the global free energy minimum. Now, this is nice because it means that you can bound any cost function above, any cost function that is strictly positive and finite. You can express as a negative log probability of a generative model, and you can bound it above by F. So basically, any optimization of a cost function, pretty much, you can bound that cost function above by F, and so you can optimize F instead. So now I'll define the free energy principle. So this is a theory that attempts to describe the dynamics of biological systems. And it says that biological systems follow a Hamilton's principle of least action. And the action that is minimized is the path integral of the free energy that depends upon your approximate posterior, so your inference over external states, and your blanket states, your sensations and actions. The blanket states are a stochastic process. So this is basically saying that biological organisms update their model of the environment so that their inference is always as good as possible, so that they always have the best possible representation of the environment according to their sensations. And this below are the Hamilton's principle of least action equations. So the reason why I'm interested in this theory and what I got into this field in the first place is that many key brain theories can be reformulated as minimizing free energy. So I won't go through them in detail, but I'll just mention a few of them. So the negative free energy or evidence lower bound is a lower bound on the log model evidence. And this log model evidence can be reformulated as a reward function or a cost function. So then you get that optimizing free energy is the same as optimizing value, which is something that you encounter in reinforcement learning, optimal control, and so on. If you take the negative of this expression, then you get other theories like Infomax principle, minimum redundancy, and so on. You can also take the expectation of that relation and you get the homeostasis, for example, which says that the entropy of your blanket state, so the entropy of your sensations and actions, remains bounded. And lastly, when you're minimizing free energy, you're approximating the true posterior. So approximating what is actually out there, given your data, having a good inference. So this is also like Bayesian brain, evidence accumulation, predicted coding. So my motivation is to be able to derive the free energy principle from stochastic dynamics, to try to give some a mathematical justification of why the free energy principle works. So my starting point is a very simple, naive model for biological systems, which consists of 4 coupled stationary diffusions. So by diffusions, I mean stochastic differential equations on Euclidean space, driven by independent Brownian noise. So before I move on, let me just say the limitations of this work is that the stochastic processes that we consider here are not very general. They're stochastic differential equations with independent Brownian noise. So now we're working on generalizing our results to correlated Brownian noise and then hopefully to more general stochastic processes. So this model is very naive, but on the other hand, what is nice, I think, is this coupling between the differential equations. So basically you have internal states that give you the dynamics of what's inside the brain, or that model what's inside the brain. Then you have sensory states that model the dynamics of your sensations, active states model the dynamics of your actions, and then external states model the dynamics of the environment. And all these variables are coupled, except internal states cannot directly influence sensory states, and external states cannot directly influence active states. Right, so just for later, IT are the internal states, so stochastic process, ET, external states, AT, active states, FT, sensory states, and VT are the blanket states. So now I'll go to the results and how we can derive the free energy principle from that model of dynamics. So I won't go into the results in detail, and I won't talk about the assumptions because they're mostly about things being well defined. I'll just go through the results very quickly. So supposing that these 2 distributions have a unique global maximum, we can define at each time a most likely internal state and a most likely external state. And we have a synchronization map sigma that maps every internal state to the corresponding most likely external state. So you have a correspondence between internal states, what's inside the brain, and external states, what's in the environment. And then you can define distributions Q such that internal states parameterize approximate posterior distributions over external states. So now you can define a free energy scoring the fit of those distributions as a true posterior. So the free energy is basically going to assess the fit, the goodness of this distribution Q as a posterior for what is actually going on in the environment at each time, given blanket states, so given sensory data. And so the result is that the most likely active states and the most likely internal states are gradient flows that minimize the free energy. So the nice thing, I think, is that from a very abstract setting, we're able to recover dynamics that are consistent with variational inference and with free energy minimization. And one open question is whether this is actually a least action principle on free energy. So this we don't know. So now we can look at the dynamics on path space by fixing some time t and looking at paths from time 0 to time t. And the result is that if you set pi to be the agent state, so internal, sensory, and active states, then you have a function g of path, which we call the expected free energy, that scores the expected divergence between predicted external states and target external states, or stationary external states, however you want to call it. And then that has also an ambiguity term, which scores the expected entropy of the agent state. So this hopefully will become clearer in the last part of the talk. Now, the core result is that the most likely path of internal states minimizes expected free energy, minimizes this quantity G. So thanks to this proposition, we can extend those dynamics that are consistent with inference into the future. And so now, in the last part of the talk, I'm going to present how we can use these ideas to simulate behavior in a framework that's similar to Bayesian reinforcement learning. This framework is called active inference, and it consists of applying the previous principles to simulate autonomous behavior. So there's a simple three-step recipe to create an active inference agent, which is to give it a generative model of the environment, then fit the model to observations by minimizing free energy, and then choosing actions that minimize expected free energy. Now, what's really important is that optimizing expected free energy in action selection balances exploration and exploitation. And of course, active inference is very similar to certain forms of Bayesian reinforcement learning. Right, so I thought the best thing was to show you a video of an active inference agent, but I need to change. So basically the video is on a different screen, and I need to share that screen, but I don't know how to show it. So I'll just post sharing and share a different screen.
Yeah, that could work.
See if that works. Right. Does that work? No. Does that work?
Yes, and now there's something moving.
Okay, very nice. Right. So this is an arm that's moved by an active inference agent. So here we give basically a hierarchical model of the agent, to the agent. So this is the model of the environment. And basically, by minimizing free energy and expected free energy, the model the agent makes the predictions of the model true. So it basically fulfills the predictions of the model. So the discrete level 2 is a Markov chain that says the black dot where the arm needs to go is going to be there, there, or there. And then the discrete level 1, depending on where the black dot is, it specifies intermediate steps or where the arm needs to go in order to reach the black dot. And then the continuous level, so this is based on stochastic differential equations. The discrete levels are Markov chains and partially observed Markov decision processes. And basically the continuous level gives the continuous dynamics in order to reach the locations. Okay, so now I'm going to go back to my talk. Can you see my slides now?
Yep.
Okay, nice. Thank you. Right. So of course, this has applications in robotics. So now, I guess reinforcement learning is the dominating paradigm in this area of autonomous behavior. So it's important to be able to compare reinforcement learning and active inference. And so there has been a recent paper that just compared different schemes on a task where you learn to navigate a frozen lake on a modified frozen lake OpenAI baseline. So this is a platform where you can benchmark different algorithms. So I'll just talk you through the figure. On the left-hand side is a deterministic environment. So well, what I mean by deterministic is that the environment doesn't change over time. And on the x-axis is time, and on the y-axis is the average reward in 200 trials. So as you can see, active inference performs extremely well, and the next best algorithm here is Bayesian reinforcement learning. But then, as you can see, if you give active inference a null model or a generative model that is basically not fit for purpose for the environment, then active inference performs at chance. So this is important to bear in mind. And then the stochastic environment. So stochastic environment means that where you see the vertical lines here, this is basically a time where the environment changes. So the structure of the environment changes at different times. And as you can see, active inference is extremely good at recovering. So it's extremely adaptive. And of course, active inference with a null model doesn't work well. So it's important that active inference has a good space of models to optimize free energy over. And I'll just conclude with reward maximization of active inference. So active inference seeks to solve the following problem. It is to select actions so as to reach and remain at a target distribution on state space. So if you're in a reinforcement learning task, you have a reward function, and you can specify the target of the agent to be a Dirac distribution of a reward maximizing state. And then it's possible to show that active inference provides the optimal solution to the Hamilton-Jacobi-Bellman equation, which means that active inference gives you the optimal solution in terms of reward maximization in the task. And this is for finite horizon Markov decision processes. So I'd like to thank you for listening, and special thanks to the organizers of the conference for the opportunity to speak. And I also like to thank my supervisors, Greg Pavliotis and Carl Friston, and my funders. And here's some references if you're interested.
Thank you, Lancelot. Do we have any questions? Any questions? Margaret, the question.
Thanks for your talk, Lancelot. It was really good. I was just, in various places you talk about reinforcement learning, and I wonder if sort of learning, like modeling the, like thinking with the brain in this way can change the way we might think about sort of doing machine learning in other ways. This balance of exploration and exploitation comes up quite a lot, and I wonder whether some of your work could be sort of applied to that sort of thing. I'm not sure I made sense.
Yeah, it does make sense. I think it's a very interesting question because, as you say, I mean, it's a main problem in reinforcement learning of how to balance exploration and exploitation. And most algorithms, they either don't have any exploration, at least traditionally, or more recently, people add just like ad hoc terms in the objectives, such as like maximizing the mutual information between your representation and your representation of the environment and the environment, or things like that, or just random exploration. And it's true that this framework has, I mean, the theoretical nicety is that you get the exploration for free. Now, I would say that, I mean, it's not necessarily, this is not really an alternative to reinforcement learning per se. The thing with reinforcement learning is that there's so many algorithms. It's not very well unified. So there's so many algorithms that when you're comparing active inference with reinforcement learning, you can just test a subset of the reinforcement learning algorithm. So you can never get a complete picture about whether active inference is better or not. And I'm sure you can find other tasks where maybe active inference would perform worse. But I think active inference, yeah, gives you the exploration for free, which is nice. And then it enables you to think about reward in a more flexible way, which is that here the goal is to select actions to reach and remain at a target distribution. So it's not just maximizing a function, but it's like reaching a distribution. So maybe your target distribution is a Gaussian on state space. And so you will select actions so that you visit your state space according to the Gaussian by sampling the Gaussian. So I think it's just an alternative point of view that can be useful.
Yeah. That's interesting. Yeah, thank you for your talk.
Thank you.
Do we have any further questions? Okay. If not, I'd like to thank Lancelot for your talk.